So our next speaker is John Hill. Yes.
Great. Thank you. So I'd like to thank you for the invitation, first of all, to speak to you all today. It's a great pleasure to be here. This is not my natural community. I'm a condensed matter physicist, but I'm very happy to be here and talk to you all and represent Brookhaven. And I'm really happy to follow Marcel's talk because I thought that was a perfect introduction to what I'm going to be talking about here, which is the programs at Brookhaven. But there's, again, that synergy between the particle and nuclear physics, the high energy physics components. So this is really good following. So thank you, Marcel. I thought I'd start with just a very high level view of what Brookhaven is, who we are. We're about 3,000 people. We have some big accelerators, both the Collider and the Light Source. And so we're very big on our user facilities. We have over 4,000 guests a year coming through right now. We're just under $1 billion in funding, almost all of which comes from the Office of Science. Nuclear physics is the biggest single program within the Office of Science at Brookhaven. We have $300 million of funding a year from them. Our second biggest is BES, which funds the Light Source and other activities. I'll talk a little bit about that. And high energy physics with $100 million is our third largest program. So really important to the lab and what we do. And I'll tell you some highlights about what we're up to in the high energy physics program in the next 20 minutes or so. Before doing that, I wanted to put the context of the overall science program at the lab. We have four big science initiatives. The first is understanding the building blocks of the universe. That's, of course, where the high energy physics and nuclear physics programs reside. It's about our collider. It's about our high energy physics program, beyond standard model, things like that. And that's the one I'll talk most about today. The other initiatives, we have one in leading in discovery in light-enabled science. That's driven by our light source. We plan to complete that light source in terms of the number of beamlines, building out and ultimately upgrade the light source. Its programs are focused a wide range of activities from energy storage to catalysis to microelectronics to plant science. And so that's our second initiative. The third one is in developing next generation information science and technology. That's quantum computing, where we have a very strong quantum computing center funded by the Office of Science. It's looking at energy efficient materials in microelectronics, and the big AI initiative is led out of this piece of the lab agenda. And I'll talk more about AI in a second, of course. And the fourth initiative is advancing energy security and essential resources independence. This is where we have activities protecting the bioeconomy, energy security, so that's grid resilience, it's energy storage. And we have an isotope production facility producing radioisotopes for therapies and diagnosis that really is a critical piece of the DOE's mission to meet the nation's needs in isotopes. So those are the four initiatives. Now I want to dive down into talking more about the first the high energy physics component and then the nuclear physics component. Before I do that, it's worth mentioning the Genesis mission, which we've just heard from the previous speaker and others, that this is a really important activity within the DOE. It's been launched in the last few weeks formally. And it's all about securing US leadership in AI for science, for energy, and for national security. So it's going to harness the power of AI, of course, but particularly the capabilities at the national labs, the large data sets we have and can generate, the experimental facilities we have, and the supercomputing facilities. So integrating those together in a single platform to carry out those science missions, to carry out the energy mission and the national security mission. So Brookhaven is a big piece of this, of course, as are all the national labs. We are working with our industrial partners to play key roles in these areas. Particular focus for us right now is in advancing microelectronics, so new materials for microelectronics devices, new ways to process information. For the securing the electric grid, so making sure AI can be applied to keeping the grid resilient, reliable, secure, things like that. And then perhaps of most relevance to this community is applying AI to our accelerator operations, to optimize the experiments running on our accelerators and to do the data analysis. So we're in a unique position. We have a large set of data from our operating machines, from both the light source and the collider, that we can train AI on, both operating the accelerator itself and then the experimental data that comes out of the machines. And so the idea here is to train foundation models on this data set so that we can operate our machines much more efficiently going forward, tune them up faster than perhaps a human can, or perhaps even run them in modes that we wouldn't think of to run, where we can optimize for a particular signal from a particular experiment. So that might be a collider, it might be a light source. There are real opportunities here to take advantage of the AI, the power of AI to advance our science. So that'll be a big piece of what Brookhaven does. We have the light source, that's NSLS2. We have our nanocenter, and we have the RIC collider, all of which have produced large amounts of data that we can use for these kind of activities. And then leading into the EIC, of course, really important in the future. And I'll come back to some of these themes later on, but I wanted to mention that up front, given its importance. Okay, so diving into the high energy physics program, we have a very strong particle physics program here. Hopefully, most of you are aware of this. We're the lead lab for the US Atlas program, for the US Bell program. We're a leading contributor at Dune, part of the Rubin Observatory, where we were part of the fabrication of the detector, slight detector devices. We're part of the operations, and of course, we're part of the science. We have an accelerated test facility here at Brookhaven. It's a unique facility funded by HEP that has both electron beams and light beams available for our users to come in and use. Particularly, the light beams are petawatt scale energies in the infrared and near infrared, something that's very unique in the complex, and encourage all of you to come use those. Strong contributions in theory, detectors, and accelerated R&D, and we'll talk more about that. And of course, thinking about the future, we're involved in thoughts about FCC and the muon collider that's being thought about actively at Brookhaven right now. In terms of the energy frontier, again, I already mentioned Atlas. We're a key component of that and looking forward to the upgrade of LHC. We are part of the accelerated upgrade project. We, in fact, lead the LHC piece for the US. We're testing the superconducting magnets for that upgrade right now. We've been through 23 of the 24. The last one's on the stand right now. Hopefully be done in the next month or so. Get it fully trained up, and then we can ship it out. So that's been a big success for us, and we're happy to be part of that project. And then, as I mentioned, looking forward to the Higgs factory at CERN, the FCCEE, and then even beyond. And we're leading the US efforts in thinking about that from the physics side and the detector side, and part of the accelerated R&D, where we see synergies with the EIC R&D that we're doing right now. For the intensity frontier, I already mentioned Dune. We're committed to successfully delivering Dune and our deliverables to Dune for the fire detectors. That's something that's really important to us and the nation, that Dune be completed successfully. We're part of the short baseline program at Fermilab, where we have lead roles in the operation and data analysis. And results shown here on the bottom right is the recent work that we led in terms of the analysis of the microboon data to show an exclusion for the sterile neutrino hypothesis. And then, as I mentioned earlier, we're part of Bell 2. We are the leader for the computing for that. That data comes to Brookhaven, where it gets analyzed in terms of understanding the charm physics. And we house the computing here on site in our data center. On the cosmic frontier, we are part of the Vera Rubin telescope in Chile. I already mentioned the sensors that we developed here and shipped to SLAC to be incorporated in the telescope. And now we're concentrating on the first science results, understanding those. We led the DOE component of the Lucy Night program. This is a mission to put a lander on the far side of the moon and operate it at nighttime there to look for, or to at least see if we can, if it's feasible to look for signals from the dark ages in such a geometry. That lander we launched towards the end of this FY20 calendar 26. So looking forward to seeing that up on the moon and operating. And we're developing proposals for new experiments that will be supported by the P5 process. And I'll say a bit about that in a second. So this is the chart that I'm sure you've all seen from P5 in terms of the various different projects that are going to be active over the next 10 years or so. And the green ticks here mark ones that Brookhaven either leads or is heavily involved in. So really engaged in that whole process and actively supporting it. So back to the theme of the connection between high energy physics and nuclear physics, or more generally, our high energy physics program is well integrated into the lab as a whole. I'll talk a lot about electron ion collider in a second. But on the theory side, of course, there's strong synergies between the nuclear physics and high energy physics efforts. Our accelerators tie everything together here at the lab. So we have the isotope production. We have a facility to look at space radiation effects, which is incredibly important for understanding microelectronics that you might want to launch up into space, but also biological studies. NASA does biological studies there to protect our astronauts. And industrial applications of those facilities and the tandems that we have here are very active. We have a superconducting magnet division here that's actively building magnets right now. Will be a big part of delivering EIC. We have a strong instrumentation division working across the lab with physics and others on detector technologies. You just heard the kind of impact that has on the X-ray detectors, and that funnels through to other areas of physics. And our data center here at the lab hosts computing for, as I said, LHC Atlas, and Bell 2 and others. Our light source data goes there. So we have pretty strong computing. And our quantum computing effort is very strong. We're funded by the Department of Energy for a center we call C squared QA, which is all focused on superconducting qubits, particularly tantalum-based superconducting qubits, where we've made big advances there in terms of lifetime of the qubits themselves. And the lab, of course, is tied into national initiatives. I already mentioned the Genesis and AI. We've been using AI, like many of you all, for decades in terms of understanding data. What we're seeing now is it's being moved out further upstream in the experiment, controlling the experiment itself, and ultimately the accelerators as well. And I think HEP and NP are really well positioned to take advantage of this Genesis mission and contribute to it. We're already involved, as I'm sure many of you are, in the American Science Cloud and the ModCon areas that have been started up as part of the very initial parts of Genesis, and they will grow hopefully next year into much larger efforts, and we're well positioned to be part of all that. On the quantum information science side, I mentioned our quantum computing center, where we're trying to advance the material science of the qubits themselves, but also what we use those computers for. And so analyzing quark jets coming out of RHIC, or the high-energy physics problems in terms of detecting various quantum states, quantum computers are really well suited for that kind of application. And what we're finding now is that the quantum computers we have today are not so far away from gaining quantum advantage in those fields. So that's a real goal for us over the next 5 years, to have useful calculations done by our quantum computers. And microelectronics, we have a strong effort there in terms of design, ASIC designs and devices, particularly those work at cryo temperatures is one of our expertise. And we have, through things like the light source and the nanocenter, ways to characterize 2 nanometer nodes and smaller that can't be done anywhere else. So that's a kind of combined effort in our microelectronics areas. So that brings me to RHIC. This is our collider that's been running, as probably you're all aware, for the last 25 years or so. It's made some spectacular science discoveries in that time. In terms of understanding the quark gluon plasma, we were very early in that and learning that it's a quantum fluid with essentially zero viscosity. It's a superfluid. That's something that we're very proud of. The collider itself is a spectacular machine. It can collide many different ion species, perhaps the most of any, including at high polarization, high collision rates. And so that makes it a really versatile machine. One of the other results that we take credit for was understanding that the gluons carry only a small part of the spin in the proton, and that's still a mystery that we'd like to resolve with our new machine. Which brings me to the electron ion collider. This is a collider that we're going to build over the next coming 10 years or so. It will sit in the same tunnel that the RHIC collider sits in right now. RHIC is in its last few weeks of operations. We plan on turning it off on January 28th next year, having a big celebration of all its tremendous success, and then immediately start taking components out of that ring tunnel and start getting ready to install the EIC components. So really big transition in the life of Brookhaven happening next month. As a side comment, I'll mention that the fact that we're reusing so much of the infrastructure from RHIC really brings the price tag of the EIC collider down. We think there's about $2.4 billion worth of value that's already out there installed that we can take advantage of. EIC has some very aggressive, ambitious science goals. We need to understand where the mass of a proton and neutron comes from. We know it doesn't come from the mass of the quark, so it must come from the gluon interaction, but exactly how that happens is unknown. And the EIC will probe that very directly in its science. As I already mentioned, understanding where the proton spin comes from is something that we need more data on, and EIC will provide that through its polarized collisions. And generally understanding the nature of the gluons and the saturation of gluons inside the proton. How is that working? How does it contribute to the nature of the proton and neutron and the fundamental nature of the strong force? So that's something that is really in our sights for EIC. Just some parameters for the collider itself. It's a very high luminosity machine between 10 to the 33 and 10 to the 34 centimeter inverse centimeter squared per second. It's another polarized beam machine like RHIC was with highly polarized beams, so we can get at these spin questions with a large center of mass energy range, so we can tune through the different problems we would like to understand. And again, we'll look at a wide range of species to collide. So really versatile machine with a detector, the EPIC detector being built as part of the project that will have a very large acceptance, good background, and so really a very strong detector for kind of getting at the science that we're after. There's also designed into the machine a possible second detector. That's something this community might want to think about as to what that might do in terms of high-energy physics. So that's a possibility out there for the future that I think is very exciting. There's tremendous interest in the EIC, which is very gratifying. We have 8 partner labs across the DOE complex already part of this project, 22 US universities, and a very broad collaboration group now with over 1,500 members across the world. And that continues to grow as people understand the power of EIC and the excitement behind it. So that's really, really exciting to see. This is the project timeline as it currently exists. I won't go through all the details of what this means, but happy to take questions. But the bottom line here is we're hoping to start collisions in the mid-2030s, something like that. So not so far away, actually, and something definitely for you all to think about. The point that Marcel made is that there's actually very little real distinction between particle and nuclear physics. And so that's a possibility for us to exploit as we think about what's possible at EIC, to explore precision electroweak measurements, to look for beyond standard model features, and to use the EIC to complement the work that's already underway under the HEP program. We're trying to understand exactly what we can do with the machine for these kind of questions. We've had 2 recent workshops, one focused on the beyond standard model kind of questions and one focused on the precision QCD measurements. It does look very promising, and I think that it's possible that EIC could be emerge as a facility that high-energy physics and nuclear physics scientists can collaborate on, both the science and the detector and accelerator technologies, as we already talked about. Felt like that went pretty quickly, but hopefully I got my messages across. Brookhaven has a strong particle physics and nuclear physics program. We serve a wide community, both nationally and internationally. We're deeply engaged in and leading many of the P5 activities for the future. We're at this moment finishing the last RIC run after 25 years and moving towards getting the EIC under construction. That will be the only collider built in the world in the next decade or so. Something to join into. As I mentioned, it's going to provide a wide range of beams that I think makes it a very versatile machine for addressing your particle physics questions. And again, it's not too late to join. We're looking for new collaborations and new ideas about how to use this machine once it's finished. Generally, Brookhaven has many unique facilities and capabilities. I touched on a tiny fraction of them here. Reach out to us, come and contact us, and we'll let you know how we can work with you to partner with and get your science done. So with that, thank you very much for your attention.
Thank you much, John. In the live document, we have a question from Sarah Eno for you. It says, Brookhaven has that nice NASA space radiation lab that you mentioned.
Yes.
However, it is extremely challenging for DOE-funded groups to use it. Is there any possibility of this changing?
That's a NASA facility, and they run it with a full cost recovery model. So to get time on it, you have to pay for it, for better or worse. But that's, I think, the only restriction. So if it's hard to get on for other reasons, that I'd like to understand. But it's in principle open to all. And the rate is $4,000 an hour, something like that. Not sure the exact number.
There's also just a comment from Ramona Vogt that reminds us that Brookhaven hosts the National Nuclear Data Center.
Yes.
Which provides the nuclear data that provides data for codes that model nuclear physics and high energy physics detectors.
Thank you for that, Ramona. And I think the other point to say is that there's a really important valuable resource for Genesis to train up on those data sets. So that's something we'd like to expand going forward and get more high precision data to add to that database.
In the chat, we have a question or a comment from Andy Lankford that says, please say a few words about international partnership on EIC accelerator development.
Yeah, so EIC designed from the start to be an international collaboration. We have a number of international partnerships already established with the UK, with France, Italy, South Korea wanting to be involved. I think there's over 10 countries that are signed up or about to sign up. Most of those collaborations are on the detector side. About 30% of the detector will be contributed from these international partners. On the accelerator side, it's about 5%. But we're looking for more partners. So if people have international colleagues who'd like to contribute, or please get in touch.
I don't see any further questions or comments. So thank you again, John. And we have now time for just about 6 or 7 minutes of a break. The next talk by Stefan Soldner-Rembold will start at 5 minutes before the hour. So we'll pause here for a few moments.
Thanks, everyone.
Thanks. Thank you.
Bye.